Okay, the next lab we want to talk about is Atwoods machine. We're looking at seeing friction. Okay. Now what we want to do is we want to examine tension. An Atwoods machine is actually a device to determine the acceleration of the gravity, but it uses tension to do that. Okay. So the device we're talking about is nothing more than pulleys. Okay. Now the traditional Atwoods model is one pulley. We're going to use two pulleys. It's not going to make a difference. Okay? So you have two pulleys, and from that you have a string that goes over one, goes to the next, and then comes back in. Okay? Just like that. You have mass 1 and mass 2. Now, you don't want mass 1 and mass 2 to be equal. You want one to be larger than the other. Okay? So mass 1 and mass 2 are different mass values. Obviously, if they're equal, this is a really boring experiment. Okay? Well, so one is going to be larger than the other. The other thing, in order for Atwood's machine to be successful, to be good, to be a well-run lab, is that the total mass, mass 1 plus mass 2, always stays constant. You're not introducing more mass to the system. That creates all new, brand new systematic errors that we have to account for. And we don't want to do that. We want to keep our errors simple. So what we're going to do as we progress through this experiment, and I suggest running at least 10 trials, is to grab mass from mass 2 and transfer it to mass 1. Make mass 2 lighter, make mass 1 heavier, but keep the total mass constant. You're not increasing mass. You're transferring mass. You're making one side heavier by taking from the other. Okay? And that's really, really important. If you don't do that, then this experiment is junked and you have to do it all over again. You have to keep that constant. Now I'm going to say it again, and I'll say it a third time, because every time I've ran this experiment, I always have about 20 to 40% of my students screw it up. Okay? This has to be constant. The total mass has to be constant. You're given a mass, you take all of it, you hang it on there, and you transfer. You don't grab more masses. Got it? Good. Okay. So the principle and why that this is in the tension section for forces is when we look at forces in my system, we have only two forces acting on this mass. We have tension and the force of gravity. Okay? Same with over here. We have tension and the force of gravity. Cool? Now, if this tension is less than this force, this object is going to accelerate down. If this tension is greater than this force, then this object is going to accelerate up. That's the principle of Atwood's machine. We create more gravitational force down than the force of tension, forcing it to accelerate in this motion. Okay? So what we're going to do is we're going to say the acceleration is in this direction. Cool? So accelerating up, over, and then down. Got it? Because we're going to make this greater than this. Well, in order to solve this problem, and in order to create it in a way in which we can take a good look at it, it's easier to think of it as this. Here's my mass 1, here's my mass 2. I'm just basically taking those masses and moving it this way. Okay? And I can do that because tension is that one tool that allows me to change the direction of forces. So instead of having to consider this to be down, I'm going to pretend that it's this way, and tension allows me to make that jump, if you will. Okay? So imagine that I'm pulling with a force that's equal to mass 1 times g. It's weight. Okay? I'm producing a tension in this direction once I do that. But according to that diagram before, I had tension in this direction. And even if I don't use that diagram, I still have that same premise. And then I pretend I'm applying a force in this direction. Okay? So I've got a pulling force here that's equal to the weight. A pulling force here is equal to the weight. I know that M1 is going to be greater than M2. So we're getting that acceleration in this direction. Okay? I've just taken my Atwoods machine, which is this motion, and turned it into this motion. Okay? Much easier to see. Hopefully it's much easier to see. Cool? Cool. Now, we're going to do a little bit of tomfoolery here. In order to make this as simple as possible, we're going to consider the entire system at once. Okay? Instead of what we normally do, consider this object, and compare the two. Which I can do. It's actually pretty simple to do, but there's a lot more mathematics steps, and I'm just going to skip to the end. Okay? So what I'm going to say is that the sum of the forces this way, and the sum of the forces that way, if I add them all together, I'm going to get an acceleration. So the forces this way, that's M1G, and then this tension. That's all the forces this way. Now the forces this way are this tension minus M2G. Okay? And that all produces a motion, an acceleration that's, inversely proportional to the total mass. Well, I only have two masses, so I get, and that is why mass has to stay constant. If this changes, okay, if this value changes, then you're changing both of these, which is crap. You can't do that. This total mass has to be constant. Okay? Well, look. Not important. Goes away. Okay? The tensions are not important to the total calculation. And that should make sense. If I brought these in and glued them together, I'm going to get the same principle. I'm going to get the same property. Okay? So that's not important. It's important because it allows me to make this diagram. It's important that I can transfer the force of this onto this. It's important, but it doesn't affect my calculations. Okay? So now I've got this. M1G minus M2G is equal to M1 plus M2A. Okay? Cool? I'm going to do a little bit, I'm going to erase this top line because I need the space. We're going to call this force applied. Okay? Call that force applied. So I can say force applied, which changes, because this term is going to get bigger, this term is going to get smaller. So this is a variable here. Divided by the total mass, which I'm going to bring over to this side. I'll just write it down as M1 plus M2. Okay? Is equal to the acceleration. Okay? Y equals y equals mx. Okay? You've got yourself a linear. You've got your two variables, this variable and that variable. Okay? You got your x and you got your y. So plot it. So keep changing your applied force by moving masses from M2 to M1. Record the acceleration that's being produced, and you've got your equation here. Okay? Cool? Does that make sense? Now, if we were solving for gravitational, you'd take this step, you'd pull it out, and you would have G over here. You'd have M1. Screw that. Let's do it that way. Let's do it this way. So you would have M1 minus M2 G over M1 plus M2. Okay? Cool? Yeah, that makes more sense. Let's do it that way. Let's do it the old way. We used to do it in Metro a different way. We used to solve for the slope being the sum of the masses. But this makes a little more sense, doesn't it? Okay, so now I have y equals mx plus b again. I want this to be my x. No, I want this to be my n. Duh. This is my variable on the x. This is my variable on the y. Okay? So if I do a substitution, I'm going to say that y is equal to the differences of the mass. Okay? I'm going to say x is equal to my acceleration. So I end up with my slope being g over m1 plus m2. Okay? So y is going to be the differences of the two masses. I'm taking and transferring, so that could be the same difference every time. I get in a different acceleration, and I end up with this. Okay? Well, it's not, no. If I start off with 100 grams and 50 grams, I transfer, yeah. You got it. Okay, I'm going off on a tangent there. Cool? So now you can solve for g and compare it with the actual value. The cool thing about this too, though, is that it's really, really simple to look at the systematic errors. Okay? So I'm going to go ahead and write this up on the top. Y equals m1 minus m2. X is equal to my acceleration. And my slope should be g over m1 plus m2. I'm going to redraw Atwoods machine so we can look at the errors. This is a great lab for error analysis, at least looking at the systematic errors. Here's my apparatus. I said there were only two forces in my system. I said there were weight, and I said there were tension. So weight down, tension up, weight down, tension up. That's it. Perfect system. But it's not perfect. You have your acceleration this way. Guess what? You have the force of friction that way. Both of those pulleys have friction in them. And it's not on the contact between the string and the pulley. It's at the bearings. Those bearings have friction. So there's friction there in the bearings. So what I end up when I talk about the sum of my forces is that I forget to include my two frictions. Okay? The frictions at the bearing, those are completely ignored. And they shouldn't be. They should be there. It turns out that these two frictions don't really matter. They turn out to be this. My B. My y-intercept. They should be my frictional values. Cool? Systematic error. It's going to take my graph and I expect it to hit 0. But it's going to shift it up. And why? Because I forgot to account for the frictions. I don't really care. I just shifted my graph up. What I'm looking for is the slope. As long as this isn't affecting my slope, it's not a problem. Cool? Got it? The other thing, the other problem is that I said all the mass that I'm moving is m1 plus m2. It's not. This string is mass. This pulleys are mass. So when I calculate the total mass for my slope, what I got here is I fail to account for the pulley mass and I fail to account for the string mass. Right here, this number is incomplete. I have other masses in the system. So it's going to affect my slope. It shouldn't affect it that much, but it still will. Because this is a rotational motion, they have low rotational inertia. The strings, if you use big enough masses here, the strings should have almost negligible mass. Got it? That is Atwoods machine. And that's how you do it.